Back after a short break. Now I'm with Wojtek Kuberski, who is co-founder and CTO at NanyML. And Wojtek today will show for us how to estimate model performance without target data. And as the title said, it is possible. And don't forget that the chat is yours. So if you will have any questions to Wojtek, so just put on a chat during the presentation, and at the end we will have short Q&A session. So Wojtek, the stage is yours, so let's make a show.
Thanks for the intro, Mateusz, and let's get started. So yeah, let's start with the agenda. So what we're going to talk about today is 4 things. First of all, why should we even care about estimating model performance? Why model performance matter when you deploy your models to production? Can't you just use your test performance as your model performance and go with that? Then we're going to cover 2 main causes of why your model performance can drop once you deploy your model to production. And then we're going to cover the kind of main part of this presentation, which is how we actually can and what is the intuition behind the algorithms that we developed at NanyML that are available in our open source package that you can actually use to estimate model performance without ground truth data, without the target data. And we're going to cover both algorithms, one for regression, which is called DLE, direct loss estimation, and for classification called confidence-based performance estimation. So let's get started with the first most important question. Let's start with why. Why does model performance matter? So basically, when you deploy a model to production, you would like to know what's going on. And the first thing that you'd like to know and would like to ensure is that the business impact of the model is there. And business impact is generally proxied or approximated by some kind of technical metric that you use to evaluate the performance of the model when you were developing it and iterating on it. It can be something like F1 score or precision and recall, or ROC-AUC for classification models. It can be something like mean squared error for regression models. Or maybe if you're lucky, you actually quantify the business impact in money. And in any case, you would like to know what is this business impact, and you'd like to make sure that you are maintaining or even improving this business impact of the model in time. Secondly, you'd like to know what is the performance of your model, because if performance drops below certain points, you might suddenly start losing money, exposing the company, the entire company or the entire department to additional risk. And lastly, if you know what is the performance of your model and you can show other parts of the department or maybe the business stakeholder what is the value that you're bringing, this of course also increases the visibility not only of the model but also of yourself, of your team, and that hopefully will bring you more budget, team expansion, maybe opportunity for advancement of your career. So these are the goals. This is why model performance matters. And where does it kind of sit in the flow? So model performance or performance monitoring is something that we'd like to start with for the reasons I already mentioned. And also, if we know that something is going wrong with performance, this is the only truly actionable trigger for finding out what exactly is going on and potentially taking model off production or spending our precious time and trying to figure out what exactly went wrong, which then do as part of root cause analysis. And then kind of the last part of this process is to issue resolution. So basically to be able to find what are the causes and then resolve them in a way that satisfies the goals of the ML monitoring flow, so maintains business impact, reduces the risk, and increases visibility. And just to fully drive the message home, the last part of why performance is monitoring is that it is a proxy for business impact. It identifies potential issues, because if we see a drop in performance, we know that there is objectively a potential issue with the model. If anything else happens, you'll probably find you're still driving business value, you still have business impact, and you can, working on other things. But if there is an issue with performance, then you know that you should actually start doing something. And that something is generally a root cause analysis, to trying to figure out what is the actual cause, ideally actually from actual causal setting or causal approach of the drop in performance. However, of course, we cannot just do performance monitoring if we have no access to ground truth data. And this is rarely the case, because the ground truth data is either delayed, if we're trying to make predictions far ahead, or sometimes not available at all. Take predictive maintenance, for instance, when you will never know one class or one part of the confusion matrix, because you will never know whether your whether your maintenance was truly necessary, and whether the machine would have kept working anyway. Or the same for credit scoring. If you don't give a person a loan, you will never know whether that person would have defaulted on that loan if you had given it to them. So we sometimes never have access to ground truth, and because of that, we cannot just compute performance, and we need to estimate it. How? Basically, that's just a very simple kind of manual decision tree in a way, where we want to do performance monitoring. How do we do it? Is ground truth available? If yes, we can just calculate performance. If no, because it's delayed or partially not available or fully not available, then we need to estimate performance. And then depending on what type of supervised model we have, or what kind of supervised learning we are solving with our model, if we're going for the classification, we're going to use CBPE. If we're going for the regression model, or we're dealing with a regression model, then we're going to go for DLE. So that's kind of the rationale why, and a bit of how to do it. Now, let's talk about the actual main causes of why performance can drop, and why we can just assume that the test performance is constant and the model will keep on performing at the level of test performance forever. So to do that, we need to go back to the basics, and let's consider what do we actually try to do when we train a machine learning model. Let's keep it to supervised context, and let's keep it as here, for example. Let's say we have a simple classification model that only uses one feature X, that is here. And then based on that feature X, we observe the frequency of positive and negative classes. As feature X increases, we see that there is more and more negative classes in this kind of sigmoid curve. This is the true pattern that exists in kind of objective, unknowable reality. It's there, and we sample the data that basically forms our sample. This is maybe the entire data we have for training, entire historical data, entire data we have for training, validation, testing, whatever our sample that we have access to is, this becomes basically our data. And we see that there is certain balance of positive class and negative class that depends both on the true pattern and the sampling mechanism. If we sample from different region in that space, the class balance is going to be different. If the true pattern looks different, the data is also going to be different. And these two components, the true pattern and the sampling mechanism, are unfortunately not constant. So what happens if the true pattern remains unchanged, but the sampling mechanism changes? So we're not sampling from the same region in the exact same way, but we're sampling from kind of a different place in our model input space, on our feature space. Might mean that, for example, for credit scoring, we're sampling from an older population, or population that's richer than before. That means, of course, that our data distribution will change, but not only that, but also our class balance will change, and potentially how hard it is to predict whether something is from a positive class or negative class might also change. Imagine that instead of going to a new sample that's a bit more to the right, the sample moved a bit to the left, and there was more data in this region where it's basically impossible to tell whether the given point belongs to positive and negative class, and it's just basically like a coin flip. Then your model would not perform as well as it used to, because there's just less information that allows you to distinguish between the positive and the negative class. So that's why performance might change if we experience covariance shift. And just to define it a bit more formally, covariance shift is a change in the joint model input distribution. So we want to frame it in terms of probabilities, is the P of X, where X is the joint model input distribution. So that is the first reason why your model performance can change. Of course, your model performance may change, but doesn't have to change due to covariance shift, because the data might just move to regions where it's still easy to make the predictions, or even easier than before. And in that case, your model performance would actually increase. Now, let's talk about concept drift. Concept drift is change in the true pattern. So here we're assuming that our sampling mechanism stays constant. Of course, both might change at the same time. But just to talk about pure concept drift here, we see that the true pattern is changing. It used to be this kind of sigmoid. Now we have a straight line. And that, of course, will also influence how our data looks like. And if that happens after we deploy model to production, we may again assume that your model performance will drop, because the pattern that model has learned on the training data and was validated on the validation and testing data is no longer true, does no longer hold in reality. So the model will not be as performant as before. And that is the second main reason why your model performance might change in production. So again, let's define it formally. Concept drift is the change in the relationship between the target and the model inputs. So it's the P of Y given the joint model input distribution given the X. Okay, so now we covered the two main reasons why the model performance might change. Now let's focus on our algorithms that basically take into account those changes, or to be more specific, take into account covariance shift and fully quantify the impact of covariance shift on performance. We're going to start with regression. We're going to start by talking about what is this algorithm about, what does it do, what does it allow us to compute. Then we're going to build a bit of intuition about how it actually works. And then we're going to finish with kind of a recipe or a pseudocode, but on a very high level of how it actually works. So what can we estimate with DLE? We can estimate any regression metric that can be computed on instance level. So squared error, then you can take a mean of that and the root of that. Absolute error, then if you want to aggregate it, you can take a mean of that. Maybe logarithmic error, basically any kind of error as long as you can define it on an instance level. So one specific metric that currently is not supported by DLE is R squared. Everything else can be computed with DLE. That's it. That's what it estimates. What does it do? It captures the full impact of covariance shift on performance. So then we actually know whether covariance shift has impacted performance, in what way, whether it was positive, negative, or it's a kind of a wash. It assumes that we have no concept drift. To measure the concept drift, at least at the current time, as of today, we do need access to ground truth. So we just need to roll with the assumption that there is no concept drift. And we also assume that there is no very strong covariance shift to previously unseen regions. By unseen regions, I mean the regions that were not represented at all in the training data, because then it's hard to really quantify what is the potential impact if the data moves to a place that we know nothing about. So that's kind of the premise. That's what we want the algorithm to achieve, what we set out to achieve, and we see that we actually succeed in doing that. Now, let's be a bit more practical. What are the things that we actually, if we want to run DLE with NanoML, what do we need to provide? So the first thing is we need to provide the actual predictions. For the test data, which we're going to use as our kind of reference data set, that we know everything was fine, we will also need to provide the target data so the algorithm can actually learn what is the pattern. And I'll explain what pattern this algorithm is actually learning in a second. We need to specify which metrics we want to use, and we also need to provide all the model inputs as columns. And that's it. And it's important to notice again that we don't need ground truth for the data we're analyzing, so-called analysis set. We only need to provide the ground truth for our reference set to make sure we kind of calibrate the model correctly. So that's what it takes as inputs. When it comes to the outputs or the results, it outputs a data frame, but it also can output directly a plot, so you can visualize it easily. And what we see here is the estimate metric. So let's say MSE. We have the confidence band, which is the expected or actually standard error of the estimation based on the size of the sample. So we're going to aggregate a group of metrics by day, week. Maybe we're going to aggregate it with, let's say, 5,000 units at the same time, so 5,000 predictions at the same time. So we get slightly better, let's say, statistical guarantees about the correctness of the estimation. And based on that sample size, or the chunk size, as we call it, you're getting the confidence bands. We also get the threshold, which by default is automatically determined by the variance of the data in your test set, or variance of the metric in your test set, but you can set it to any value you want. And this allows us to basically set alerts. If something really goes wrong, then we'll be able to know that there is an issue, and we can determine kind of in augmented or automated way that we need to look at what's going on with our model. Now, let's start slowly building up the intuition of how we can actually predict or estimate performance without ground truth data, and how is it possible to do it? One kind of misconception that I saw a lot of data scientists, including me, a bit more than 2 years ago had, is that all the information that's relevant for the target and for the model is already consumed or used up by the model to predict the target. But it turns out that this is actually not the case, and the question of predicting the estimated loss, so unsigned metric that kind of tell us what is the expected loss of a point prediction compared to the distribution we're seeing, is not really used by the to predict the target, to give you the point prediction, and it's not even useful for that. So let's start with an example. We have, again, just one feature, feature one, and we try to predict the target. This is a regression problem now, as we're dealing with DLE. And we see that the model, whatever model we fit, as long as it's at least a bit expressive, it's going to find this best fit line in pink, which is the point prediction. And it uses all the information data, and it predicts the target basically as well as possible. However, as you can also see, as we move to the right and the value of feature one increases, we will also see that the performance of the model decreases. The estimated loss, or the standard loss, estimated loss of that model will increase because the data is more dispersed. And this is really the key insight, that the dispersion of the data, or the difficulty of predicting in any given region in the model input space, is not information that's used by to predict the target. It's kind of orthogonal problem, and we use it, we calculate that, and we actually learn this dispersion in every single place in your model input space, and then we use that to estimate the loss and to estimate the performance of the model. So this was kind of 1D example in a very simplified way. It might be obvious. But now imagine that we have, instead of just 1D, instead of 2D that we see here, we have 1,000 dimensions. Of course, for that, we will need machine learning, and we'll need to make it work reasonably well. And how then, I mentioned this aggregation, that we need to aggregate multiple points together. The reason for that is, of course, if we measure dispersion, we might just get lucky and be very close to the real prediction or not. So we need to take, let's say, a few thousand data points to really get good estimation of what is the average representative performance of the model at given point in time, or given period in time. And now, how does the model work in practice? So we have our test data, we have our so-called reference data set, and we see that the data points are distributed in some way. We have regions where the model is very confident, so the dispersion is low, and we have regions where the model is less confident on the left and on the right. It's kind of ears. And as we deploy our model to production, we experience covariance shift. The data distribution of our model input changes, the joint model input distribution changes, and we see that there's simply more data points where feature one is high and feature two is also high, and they land in this part of the input space. And that means that the model is not confident there. So we expect there to see a higher loss for each of those predictions on average. And then if we just aggregate over all these points here, for each of those points, we're going to estimate the expected loss. We can then aggregate it, and we get the expected loss for all those data points for the entire chunk of data. And the more points we have, the more confident we can be that this estimation is correct. And this confidence is also expressed in the confidence bounds that I mentioned before. So these violet parts here, which are based on computing the sampling error. Okay, we're almost done with the DLE. So now let's just quickly go over the algorithm. The algorithm is really quite simple. The first thing we do is we calculate the loss metric on our reference data, so on our test set. We calculate it on instance level. Then we take another model, so not the model that you're using to predict your predictions, your point predictions, your target, but we train a new model that estimates this loss metric, whatever it is, let's say squared error, using the features that the model is using and the model outputs, the model predictions. And turns out that there's enough information, and we can actually directly estimate this expected loss or the dispersion in every data point and every point in the model input space. Then we do the aggregation, as I already mentioned, and we can directly estimate errors on the analysis data for every chunk, every aggregation of points, however we choose it. That's DLE. That's how our regression model looks like and works. Now let's talk about the classification. So here we're going to use kind of similar approach, but it has one very important difference, so I wanted to talk about it separately. So we calculate basically any metric you want, anything that's based on confusion matrix, like precision, recall, accuracy, etc., etc. ROC AUC, confusion matrix itself, any kind of business metric that can be calculated, or business impact metric that can be calculated based on confusion matrix. So if you know that you're losing, let's say, $5 or €5 or for whatever currency for every false negative, then you can just encode it. And if you provide this kind of metrics of profit and loss per the type of error and type of prediction, then we can also estimate that. So business impact can also be estimated with CBPE. What does it do? Exactly the same thing. Captures the full impact of covariance shift on performance, assumes there is no concept drift, and assumes that there is no strong covariance shift to regions that were not represented in the training set at all. Very similar DLE, so I'm just going to go through it a bit faster. When it comes to the inputs, again, it's quite similar. There's only one key difference here, is that we consume both the model predictions and the model scores, which if you use, for example, scikit-learn, they will be the predict probas here. So that's how we call them. And we need to have the target, but again, only for the reference data. We also need to specify whether we're dealing with binary classification or multi-class classification, as DLE also supports multi-class classification. That's it. It outputs the exact same thing as before. We're just gonna use scale. Normally it's within 0 and 1 because most of classification metrics go between 0 and 1. 0.5 and 1 in case of ROC AUC. Intuition. Intuition is very similar, but I wanted to show it here again, just because it's sometimes easier to grasp how these regions of high and low confidence behave for classification models, because I think we're more used to kind of visualizing those. So here we have this kind of butterfly data set when we see that there is one class 1, and another class 0 on the left and on the right, and they form this kind of wings of the butterfly. And we see the body of the butterfly is kind of where the class boundary is. It's a region where it's basically impossible for the model to tell whether the prediction is correct or not, or whether the model belongs to class 0 or class 1. So the model is very uncertain there. And if we see that in time, for one reason or another, we see that the data points start moving towards this class boundary, we would obviously expect that the model performance will drop. And this is, again, kind of the key intuition behind CBPE, is that there's additional information about the uncertainty of the model that's not used and not useful to really predict whether something belongs to class 1 or class 0. Now, the algorithm itself is slightly different, because we're not going to train a specific new model based on the model inputs and model outputs, but we're going to just use the model scores or the model probabilities. We're going to calibrate those. We're going to choose the threshold that you normally choose to turn the model score into probability. We're going to find this instance level confusion matrix. We're going to aggregate it, and we're going to compute a metric. And now let me go quickly through how it actually works. So let's start with step number 1, calibrate probabilities. What does it mean? Probably some of you, or probably even a big part of you, is familiar with calibration. But for those who are not, I'm just going to give you a quick overview of what is the problem and why we need to solve it with calibration. So when you create a model, let's say it's an SVM that does classification, and we train the model, we get some kind of model score. So a value between 0 and 1. Let's assume we're dealing with binary classification to simplify things. And ideally, what we want to know and what we want to interpret this value as is the actual probability. So just to remind everyone of what is the frequentist definition of probability, is that over a long time horizon, we would expect the fraction of positive to be equal to that probability. So if we see that there is a lot of data points that are predicted to be 0.1 over a big number of those data points, we would expect that roughly 10% of those will turn out to actually be positive. But this is not the case. In reality, we see that almost all models, especially the most expressive ones, like gradient boosting or deep neural networks, which are basically the only models that are currently used, as far as I know, they are terrible at calibration. And if they say that the predicted probability is 0.2, it tells you nothing about the actual probability. So what we need to do is we need to take this line, when we, let's say, bucket these observations in, let's say, 10 or 20 buckets, and we're going to fit a regression line that just takes the predicted probability and maps it to the actual fraction of positives observed on the test set. And we basically straighten this line. And that means that on the aggregate, on the average, this fraction of positives is going to correspond to mean predicted probability. So we can assume that the small score is an actual probability. We have that. So now we see that this widespread proba, if it says 0.9, it actually corresponds to 90% chance of this prediction turning out to be positive. So we use our threshold that we use to develop our application or to develop our model, let's say 0.5, we know that this is going to be a positive class. But do we know whether it's going to be a false positive or a true positive? Turns out we actually do, because we calibrate our predicted probabilities. And because we know that this on the aggregate, on the average, corresponds to true probability, we can say that the expectation is that there is 90% chance that this data point is going to turn out to be true positive, and 10% chance that this data point is going to turn out to be a false positive. And of course, on a single data point, this expectation is basically meaningless because the variance is huge and you're just sampling one point. So we need to aggregate it. So we're going to turn it into this instance level confusion matrix when we put 0.9 in true positive cell and 0.1 in false positive cell. Then we do it to all the data points in a chunk. We simply sum it up and we get this very weird confusion matrix that has floats in them instead of just integer numbers. But it turns out this is actual expectation of the confusion matrix if we assume that our probabilities are perfectly calibrated. And unfortunately, if we experience very strong covariance shifts, they are not perfectly calibrated, but that's a story for another time. And right now, I'm just going to thank you all for listening. We are, as I already mentioned, an open source library. We also have a cloud product. If you're interested in that, let us know. And if you want to give NanoML a try, please go to our GitHub. We would appreciate any kind of support there as a star or anything else. And again, thanks for listening.
Okay, Wojtek, thank you very much for your presentation. As I mentioned at the beginning of your presentation, you can ask any question to Wojtek's presentation. I see on the chat the first question from Jan. Can DLE be applied to deep learning models, especially convolution natural networks?
Convolutional neural networks.
Yes, that's right.
I believe.
That's right.
Yes, CNS. Yeah, so absolutely. And the main thing is that it basically only takes model inputs that need to be represented as numbers. So you can just take raw pixel values. If you use some kind of embedding before your CNN, you can use that. Anything that can be represented as numbers, you can apply DLE for it. So actually, right now we don't offer very strong official support for vision models, but we already saw quite a lot of users actually using specifically DLE, but also CBPE to a certain extent with vision models. So you can do it and it's going to work, and it's going to work roughly at the same level as for tabular data. Yeah, you can.
Okay, so the question from Alicia, could you clarify the usage scenario, please? For either method, I need a subset of the data annotated with ground truth, so I can train the loss estimating model, right?
Yeah, so I'm assuming this has to do again with DLE. So indeed, here, what you need is you need, let's say, your test set. You need some kind of data set for which you have access to ground truth. test set is a general example where you always have access to ground truth, because I'm assuming you wouldn't deploy your model if you didn't actually test it on your test set. That would be a terrible practice. So you have your test set, you have target data there, and then we're going to calculate the loss metric on instance level on that test set. So for every data point there, you'll need to figure out, or DLE will do it actually for you, as long as you just provide this reference data. DLE will figure out what is the loss metric, and then it's going to automatically train a model that will estimate this loss metric using features and monitored model predictions. And then you can then use this model. It's a fitted model. It uses LGBM underneath, and then you can just use it on any new data that comes in, which generally is going to be any production data that you have to ingest.
Okay, and I see another one question. This one is from Cube. Do you know any methods of performance estimation for time series anomaly detection?
Yeah, so when it comes to time series, depending whether you want to predict a continuous value or binary value or integer value, you can use DLE or CBPE. And the only thing is that you'll have to adjust the way that your data set is structured or formatted. And basically nowadays, a lot of time series models are actually models that are normally used with tabular data. So you can again use gradient boosting to solve your time series problem. And then the way you format your data is need to be formatted basically like a tabular data problem, when you just take lagged values as separate features. So lag 1 is one feature, lag 2 is another feature, etc., etc. If you format your data like that, you can directly use DLE for your time series models. And when it comes to anomaly detection, you could basically assume that, again, it's in some way supervised learning problem, but to really evaluate the quality of your anomaly detection problem, you need some kind of ground truth, you need some kind of labeled data. So if you have part of your data when you maybe manually labeled what is an anomaly, what is not an anomaly, then you can use that as a reference data and then use CBPE, where basically you can treat anomaly detection as binary classification problem. We plan to support anomaly detection more explicitly in the future, but we're still kind of waiting for the critical mass of users asking for it. So thanks for asking for it. Also feel free to submit an issue on GitHub. That definitely gives us more information about what's the most needed feature that we need to be building.
Okay, thank you. And Karol wants to know if he can use train set for training DLE or only test set.
Using train set is a generally very bad idea, mostly because what you want to do is you want to find this to be a real, the confidence level in every data point should be representative of the real world. But your train set is going to be overfit, which means that the model is generally going to be overconfident on the specific data points that exist in the train set. So generally, you should not use the train set, you should use the test set. If you, for some reason, don't have access to the test set, you can give it a try with the train set, but then it might not work at all. So stick with the test set if you can.
Okay, and probably the last question. What business problem can be solved with this? Some business cases where we have data for training, but no data later for model validation. So what business problem can it be?
Yeah, so there is really a lot of use cases. I already mentioned any use case when you're trying to predict something far ahead. Let's say you're predicting credit defaults. If you predict credit defaults 2 years ahead, let's say on mortgages, then you don't want to basically fly blindly for 2 years not knowing what is the performance of your model. You need to estimate this performance shortly after the prediction is made. Otherwise, you might be operating a model that's really bad for 2 years, and in financial use cases that might have a huge impact on the entire organization. So that's the first part, where the data is delayed, the ground truth data is significantly delayed. Second one is in some use cases, you actually don't have access to part of the ground truth at all, because you never know whether somebody that you have not given the loan would have paid it back. So you cannot actually compute the F1, let's say, because you don't have, you don't know how many true negatives and false negatives you have, because you never gave those people the loan, you will never get data. And the last kind of big type of use cases are automation use cases, where you're trying to automate human labor with a model, let's say for document annotation, document classification, things like that, where you will generally not have access to ground truth after you deploy your model to production, because that would cost a lot of money and kind of defeat the purpose of automating that data. And even you you do some kind of spot checking and you still use analysts to maybe manually check to few percent of the documents, you still don't have ground truth for vast majority of your production data. So then you need to use performance estimation to really figure out how well your model is performing.
Okay, thank you very much, Wojtek, for your presentation and answers for all of questions. Thank you very much, all of you, for the participation in this session. Now we are starting lunch break and Data Science Summit Expo. So if you want to meet with top IT employers and see the possibilities of further development or current situation on the market, so just join Data Science Expo and IT Fairs. And as always, don't forget to rate the Wojtek's presentation using stars under the video player. So thank you very much once again, and see you after the lunch break on another session.
Thanks a lot, everyone. Bon appetit.